This is Norm Christofferson, Senior Training Technologist with Johnson Controls. In this session we will take a brief look at RTDs, Resistance Temperature Detectors, and how they work. All control systems consist of three parts: a sensor, at least one, a controller, and a control device. Sensors measure a physical change in the environment, like in temperature. The sensor changes what it measures into a signal that the controller can understand, and the controller compares the incoming signal to a set point and then makes a decision. If some heating or cooling is necessary, the controller sends an appropriate output signal to a control device such as a heating or cooling valve. In our study today, we are concentrating on the temperature sensor called an RTD. An RTD is actually just a very fine piece of wire, often as small in diameter as a hair. The resistance of wire is determined by four factors: the material it's made of, the length, and its diameter. Let's stop with those first three. Once each of these are determined, they are not going to change. We have a fixed material, we have a fixed length, and we have a fixed diameter. The only thing left is the temperature. As the temperature changes, the resistance in ohms changes. So now we have a temperature sensor. All sensors are classified as either active or passive. Active sensors require an external power supply to operate. Passive sensors do not need a power supply to work. The RTD is passive. Its resistance changes when its temperature changes, even when not connected to a circuit. RTDs are also analog. The resistance varies with varying temperatures. On the right we see three RTD sensors. The coiled one is an averaging sensor. The straight one measures along its length and can be inserted in a duct. The smallest one is an outdoor air temperature sensor and is protected from the weather by a PVC cover. RTDs have a positive temperature coefficient. We say they are PTC devices. When the temperature increases, the resistance increases. Temperature is our controlled variable. As the temperature rises on the left, the resistance increases up the ramp on our graph. This is what an RTD does because it has a positive temperature coefficient. The actual temperature to resistance values may be read from a table. This table is for two RTD materials as well as for two different thermistors. Our concentration is on the two RTDs. On the left, our table indicates temperature. The lowest temperature on a table is minus 50 degrees Fahrenheit, and the highest temperature is 80 degrees Fahrenheit. Many RTDs are made from either nickel or platinum. Let's look at the nickel RTD on the table. At 70 degrees Fahrenheit, the nickel RTD sensor has 1000 ohms. At 80 degrees Fahrenheit, its resistance has increased to 1030 ohms. I have now advanced to the next page of our table. This page extends the temperature to resistance readings to include temperatures over 80 degrees Fahrenheit. Using an ohm meter, a thermometer, and an RTD of unknown material, you could use the table to identify an unmarked RTD sensor. So there you have it, the basics of what an RTD is and how it works. This is Norm Christofferson. Thanks for watching.